Hi, from the organizer for inviting me. Good to be back in Imperial College. And let's start. Coming from the Pacific Ocean, there's the beautiful campus of UCSD. Library surrounded by Salk Institute, Scrip Institute, we have Dexcom, Illumina, Qualcomm, so a lot of digital medicine. These are the UC tattoo on the skin. So again, when I started, again, we were looking for comprehensive assessment of the individual health and wellness and nutrition. But all what we had 15 years ago is the tracking of a vital sign like ECG or mobility. We didn't have any chemical sensing, but to get a comprehensive information, you need both the physical and chemical parameter dynamically changing. We need to go beyond the vital sign to capture molecular information continuously to personalize nutrition, health, and wellness. So this is what we used to have 15 years ago when we started. A lot of electrical, ECG, EEG, motion, temperature, respiration, little blood pressure. But what was missing is the chemical, which is also the opportunity. We had a little bit glucose like the CGM started 2 decades ago. These are big needle, but we didn't have any electrolyte, metabolite, lactate, or cortisol, alcohol, and many more. So this is a big opportunity, but also a major challenge because of the nature of this issue, like stability, biofouling, and others. That's why, except the CGM, we don't have any commercial one. We have in vitro, a lot of in vitro diagnostic, all the clinical analyzers are based on this, but very little wearable. So our vision for when we meet again in 12 years, maybe we can shrink the entire lab on the skin. So this is typical traditional lab, all the aisle and benches. So can we imagine if we place the entire lab onto the skin, maybe in 12 years? And this capability will give us ability to monitor and predict any disorder and early disease, like check the engine of your automobile. So we can check the body for potential disease and disorder. So this is the vision, the dream. And the benefit, again, you can predict different potential disorder, continuous chemical information anytime, any location, done it non-invasively without piercing the blood. And it will change the way nutrition, wellness, and health are being assessed toward the self-care and distance medicine. Like during the pandemic, we have a lot of remote medicine, lower costs, and improving quality of life, especially for the elderly. So this is the vision, but we are facing major challenges, technical challenges, engineering challenges, performance challenges. This includes, as I mentioned, stability of this device. This involves enzyme or antibody or aptamer, the uncontrolled condition. It's not like in vitro, a lab condition, room temperature, the conditions are changing, temperature changing, pH of sweat is changing. We need to have large-scale validation against the gold standard, the blood assays, safety issues. You put it on the eyes or inside the mouth, under the skin, all need the FDA approval for biocompatibility. Some of the conventional assays, like immunoassays, are not reversible, are not very complex step of washing, and the antibody regeneration is not easy on the body. Issue of compliance with the curvature and the stretchability of the skin, energy, powering demand, and issue of big data processing and data security. See, these are major challenges, but especially the first 3 one. And we love electrochemistry, as Mike said. We've been doing it for 4 decades now. And as you see, we have the CGM of Dexcom, glucose. So electrochemistry satisfy many of the requirements for on-body monitoring, not only the portability, miniaturization, also high performance, sensitivity and selectivity, low cost, low power requirement, easy to use. So the moment the only commercial one is CGM from Dexcom or Abbott or Medtronic. And this is in my Nature Biotech review covering the progress of biosensor toward wearable. But the first, this was 61 years ago, the first glucose sensor. It took 5 decades of more in vitro diagnostic benchtop, YSI, moving different immunoassay, DNA. This is all in vitro diagnostic glucose strip in the late 80s. But only the last 15 years we moved to on-body measurement. So it's a nice summary. And again, you see activity now explosive, many groups, including here in the Imperial College. So if you visit my lab, you'll see this mannequin with a variety of form factor of chemical sensing on textile, on socks, on the skin, on glove, not only for biomedical, some security application, environmental. So again, for variety of biofluid and analytes, so we can try to measure many metabolite, electrolyte, drug of abuse, also pharmaceutical, for Parkinson, hormone, cortisol, insulin, disease biomarkers, cytokine, nutrition and wellness of both mineral and vitamin C and D and neurotransmitter, chemical agent, toxic metal, and so on, like this nice panda we will see. So we are focusing on a variety of non-invasive assays, or in the case of ISF, is minimally invasive. And we will focus today on sweat and ISF using, again, microneedle, tattoo, or textile. So this will be the main focus, as the title mentioned, measurement on the skin by sweat analysis, this smiley pH sensor, or under the skin from the ISF using our microneedle platform. So both sweat and ISF offer very rich biomarker chemical information that we will try to capture dynamically. So the skin is the gateway to our biochemistry, the window to our body. We can use the skin to monitor sweat, or the sweat glands coming. We can also access the ISF, either by reverse iontophoretic extraction or inserting the microneedle minimally. So we'll focus, first we will start with the sweat monitoring. We all use a printable device, stretchable device, screen printing widely used. You can see in the exhibit from Metron DSM, this is classical now, for over a decade, screen printed electrode, also the glucose strips for several decades rely on screen printing. But most of these are very rigid. One you see in the exhibit, the substrate is alumina or even air, so they are quite rigid, and we need to move to flexible one. So the way we print on textile, for example, this is the range from different injury, traumatic brain injury, soft tissue, so 8 different sensors, the black one, then the joint reference counter electrodes. So these are the printing the carbon on this. This is the silver contact. You see the silver go under. Then we have the insulator, the dielectric in blue. So you have 8 electrodes with the reference and the contact from the other side. So this is on Gore-Tex, on the textile. But the challenge, as I mentioned, the traditional electrochemical device like battery or your pH glass electrode are very rigid, very bulky, very planar. Our body is very soft and curved. If you visit San Diego Zoo, you'll see these flamingos. They are very stretchable. So we need to bridge the gap between the rigidity of electrochemical devices and the curvature and softness of biology. So this is our goal, to impart stretchability and flexibility into our electrochemical device. We use innovation in material, our printed ink, we make them enduring the stress. So this is not like conventional ink. We put different elastomer in the ink, like Ecoflex, polyurethane, to impart this stretchability. We want a device that can fold, can bend, can stretch, even self-repair. So we are modifying the ink. Also, we have this serpentine structure that can stretch, either on tattoo or textile. So we have a 2 levels of stretchability. One level is coming from the serpentine. So the serpentine is unwind, and you get the first degree of stretchability. And the second one is from the material, the ink formulation, that allow you, once you unwind the serpentine 200%, then you can stretch even more to 500% from 1 centimeter to 5 centimeters. See it on textile, the serpentine unwind, this is potassium and sodium ion selective electrode. So you can push it all the way to 500% stretchability by incorporating different elastomer into the ink, along with the serpentine structure. So you can see this, the stencil we use with the different serpentine structure, placing on a tattoo, the two working counter electrode, reference electrode, place it on the skin. This 7-8 years ago.
Yep.
Another design is what we call island bridge, where the islands are not stretchable. They are just small discs of 1 millimeter, but the bridges are stretchable. You can do it on tattoo or on textile. So here the bridges are highly stretchable. They are a stretchable silver ink, while this pellet of carbon or graphene, they are not stretchable. But the whole device is highly stretchable. If you stretch too much, you can have crack. If you do 600–700%, you have crack and you lose your conductivity. So you incorporate self-healing capability into the ink for self-repair. So these are magnetic particles incorporated into the ink. So as soon as you have the crack, you have self-repair. You have like two magnets attracting each other. In 5 seconds, you get back your conductivity. You can be repeated cracking in the same location, big cracking of 3–4 millimeter. You still repair it in 5 seconds. So we have this innovation in material. Now we can move to our skin-based chemical sensing. And again, as I mentioned, we use the screen printing, but now coupling it with the tattoo transfer technology. Like tattoo paper, we make nice device like flower electrode. This is the 3 electrode working reference and counter, or smiley pH sensor. This is the reference and counter electrode. So we have the elasticity of the tattoo along with the stretchability of the ink. And the first device, this is the way we transfer it to the skin from the tattoo papers, and we wet it, we remove this protective layer, and you get a beautiful flower. And you place the flexible electronic connected here. So this is, for example, what we will see for glucose, where we have reverse iontophoretic and sensing on the tattoo papers, and we transfer it to the skin the way we peeling the protective layer. So here this tattoo was to the reverse iontophoretic. It takes usually 5 seconds. This is slow motion to show it, and you just wet it with the deionized water, and then you remove peel out the paper, and you get the remaining tattoo, and you place the electronic here. We will see some examples for glucose extraction. So the first one was exactly 10 years ago. This was for lactate monitoring using lactate oxidase for sport and wellness applications. So this is my nano engineering department. But these are the 3 electrodes where we place the lactate oxidase on the working reference and counter. You can twist it. And again, this is in vitro calibration, 1 to 20 millimolar. And then this is during the exercise, you follow the dynamic. This is the muscle fatigue and fitness level. You see, after 10 minutes, you generate the sweat. You see the profile of sweat lactate, temporal one. This is the control without the enzyme, showing the high selectivity of the sensor. And this is during exercise activity. So this was the first one. Then, as I mentioned, diabetic is playing a major role, moving to minimally invasive, non-invasive glucose monitoring, ketone detection, maybe insulin one day. So again, aiming to measure glucose in sweat or ISF, as we mentioned, using the sweat first, where we use the same tattoo, with extracting a reverse iontophoretic extraction after the big breakfast. You see jump in the glucose, and this is with the Prussian blue mediator. You get very selective detection of glucose before the meal, after the meal. And you can see this was featured in Vienna in the diabetic exhibit a few years ago. So again, this is the printed electrode. Then you see the flexible wireless electronics. The electronic is also flexible. You place it here with magnetic attachment. So electronic is reusable. We use the tattoo for 1 day. And you can see this flexible supporting electronic, wireless, telemetric. And this one do both the extraction and the sensing. You see the flexibility and wireless communication to a phone or laptop. And then we extended it for all day operation. So this is a 10-hour, these are 2 meals here, you see following with the blood correlation to blood glucose meter. And here it's similar to the glucose watch, but the glucose watch has some problem. We lower the reverse iontophoretic current at the time, so we don't have the issue of the glucose watch. And so this is the device extraction and detection, 2 measurements per hour over 12 hours. Then we extend it to alcohol because tonight we will drink and then we will eat, so we can measure both the alcohol and glucose. Here we stimulate the sweat. This is sweat alcohol with pilocarpine. So we stimulate the sweat, and then you have alcohol oxidase to detect the sweat alcohol. So you can drink as much tonight if you don't drive, and you can see the change of the alcohol correlation to blood alcohol. And this is the control, no drinking, no signal. And the wireless electronic, it tell you you are drunk, don't drive, and this takes 3 minutes total. So later on, we can, as I mentioned, you can eat and drink. So we developed this glucose tattoo. This can measure both sweat and ISF, ISF glucose and sweat alcohol. So in 5 minutes, you both stimulate the sweat from your alcohol sensor here, and then you get the glucose extraction here. You can get both while you're drinking and eating. You see correlation to blood alcohol, blood glucose. These are control, no eating and no drinking. So this is a panda shape. One is the alcohol sensor, alcohol oxidase. Here is glucose oxidase, is supporting electronic. And this example, you're measuring 2 separate biofluid at different location on the same tattoo, sweat here and ISF here. So personal nutrition is also a recent trend. We moving for tracking nutrient continuously, like vitamin C or mineral like zinc and others. So this is again different profile for personalized. You see 4 different subjects. You take the 1,000 milligram of vitamin C, where the ascorbic acid oxidase, and you monitor every 20 minutes. Most of them peak about 90 minutes, but still slightly different profile. So this is the trend toward personal nutrition for guiding a behavioral change and personalizing this. So you can see the individual profile. Again, you see every 45 minutes a maximum, but slightly different profile following the vitamin C after taking the pill at time 0. So overall, it will give you not only vitamin, glucose, keto drink, sodium for hydration, potassium, again, following with the nutrition information for complete comprehensive personal nutrition, both sweat and ISF, saliva monitoring. We use also sweat fluidic to guide the sweat over the sensor. We have 4 inlets. Let's say during exercise, they're pushing over the detector with glucose oxidase or lactate oxidase, wireless electronic. So the sweat is flowing continuously and removed from the exit. You can see the video with the dye. The sweat is pushing the dye. We remove the sensor. You can see in 10 minutes, it's flowing completely. And then you're covering the electrode surface and you see the profile of the sweat. This is on PDMS. And you can use this is with lactate oxidase during the X-ray, different subject. Once you get the sweat entering the detector, you see the lactate profile with lactate oxidase here. So 4 inlets, sweat is flowing to the outlet. The same is for electrolyte. We have sodium and potassium ion selective electrode. Again, so this is lactate, this is the electrolyte. We can also stimulate the sweat. Instead of exercise, we do a fluidic where we stimulate the sweat here with pilocarpine, pushing the sweat over the detector. So you see this 4 inlet with the iontophoretic sweat stimulation, and it's moving it over the working electrode, like this is glucose sensing. So this is being commercialized by a Swedish company in Malmö, Innosense, that commercialized this. You see the fluidic channel for the glucose sensing. Instead of exercise or instead of stimulating sweat, you can use also the fingertip sweat. There's a lot of sweat glands, and in the fingertip, you don't need any sweat stimulation. You just touch the sensor, and in 30-40 seconds, you get the response, like for levodopa, for Parkinson monitor. So in this case, we don't need any exercise, no any sweat stimulation, just touch base, and you get, you see, you place the electrode. We also use it for energy harvesting. In this case, for glucose, you just touch it with no blood, no pain. You can get your reading in 1 minute. You have a little personalized calibration for the sweat, a one-time calibration. You correct for the variation, personal variation. You can use this calibration for 6 months. You correct for this variation in the sweat rate, and you touch it, and you get reading every 5 minutes, and the same sensor strip. The same we apply for cortisol. Here we use a MIP, molecular imprinted receptor for cortisol. We monitor you a stress level, but stressless, so stressless stress monitoring. You have the MIP for cortisol, and this have embedded Prussian blue. So the signal, the electrochemistry of Prussian blue is decreasing. You add here 10, from 1 to 10 micromolar of cortisol, the signal is decreasing due to the incorporation of the cortisol into the cavity. So this is cortisol, and same for levodopa, as I mentioned. Looking for pharmacokinetic of levodopa. Levodopa concentration in blood are micromolar. There is a slight delay between, you see the blood is in red, you take the pill, these are the 2 Parkinson patients, they're taking the pill, you see and rapidly you see the change. The sweat is just 5-10 minutes delay, but the same profile. Here you see some control without the pill or without the enzyme. Here we use an enzyme tyrosinase. The tyrosinase converts to a dopa to dopa quinone, so we measure the quinone, the product, and again, you take the pill, and every 10 minutes you follow in the pharmacokinetic of the levodopa in sweat, and it's nicely correlated. So every 10 minutes increasing, and then you have maximum at 30-40 minutes, and then decreasing again until after 1 hour, it's almost gone. And these are micromolar even in blood, so the sweat can really follow these changes almost rapidly. Now, another direction we're doing is coupling this chemical sensing with physical on a single device, developing multimodal device like ECG, blood pressure, along with chemical like glucose, lactate, or cortisol. So this is example of our BPCM, blood pressure chemical monitoring, or this is the early one, ECG-CM, so ECG chemical on the same device. So we started this 2016. So the goal is to record simultaneously the vital sign, like blood pressure, temperature, or ECG, with different chemical like cortisol, lactate, or glucose. So the advantage, again, this is the example, we want to get comprehensive information, capturing unavailable information on a single device, tracking both the physical and the chemical parameters, such as the ECG, blood chemistry, and the blood pressure chemical sensor on the single patch. So here is the blood pressure chemical sensing. The blood pressure is acoustic, it's ultrasound. And these are the chemical, you can measure sweat and ISF. So you place it in the neck because you can have the blood vessel here. And this is acoustically measurement, collaboration with Shang Chun and develop the blood pressure. But the center too, you can see this part of the acoustic transducer for blood pressure. This one is for ISF, glucose. This is for sweat lactate. So you measure sweat analyte here, ISF analyte here, and blood pressure for different daily activity. So if you exercise, you see changes of blood pressure and lactate, for example. You have your caffeine, the blood pressure going up, you can detect the caffeine. You have your cheesecake, you measure the glucose and blood pressure and so on. So here is the device. You can see very flexible, stretchable. These are the blood pressure transducer before you place on the skin. Here you have the iontophoretic, and measure sweat here, sweat lactate, ISF glucose here, and you can see the device is only 1 inch square, 2.5 centimeters square, and both the blood pressure chemical monitoring. No crosstalk, there is no cross reactivity between the chemical and the blood pressure transducer. You can see these are the blood pressure profile when you apply the potential of the electrochemistry on and off. There is no interaction. The same here, this is amperometric glucose. You apply the blood pressure on and off. There is no crosstalk, and all of this is stretchable and flexible, and you can bend it, you can twist it with no issue of cross-reactivity or mechanical issue. So it's fully mechanical resiliency. And by doing so, we can follow simultaneously. Like here is example of exercise, which increase the blood pressure. You see, you start your exercise, 75 blood pressure, go up to 110. Then you stop exercise. Sometimes you monitor your lactate. So this the lactate monitor. You start the sweat after 6-7 minutes. You see the sweat profile. Simultaneously, you see the blood pressure profile, and this is correlated to the blood lactate meter and the standard blood pressure. All correlation. So during daily activity, if there drinking caffeine, exercise, eating, you follow both of these physical and chemical parameters. The same is for our early work on ECG chemical monitor. So the same tattoo, there's a multiple of them. Here are the ECG electrode. These are the chemical one. You can do lactate or glucose. So this is one of them. They're all flexible with supporting electronic. Then you see the lactate profile. This is the ECG. During the exercise, after the exercise, and this is a different subject. So again, fully independent, no cross-reactivity between the amperometric and the ECG electrode. So we hope that this multimodality will give you more information. So we're going now under the skin. The remaining of my talk, we're moving from the surface of the skin. This was a pH sensor. Now we go to capture ISF information, which is closer to the blood, very fast partition of many biomarkers, and you have very nice correlation to blood level, and also multiplexing. You can see lactate, alcohol, glucose, you can build multiplex. This is all 12 millimeter diameter, my center CWS with all the electronic to do continuous ISF monitoring. So again, ISF is attractive compartment just under the skin. This is working from Imperial College. Tony Kess also working on this. So you can access ISF, as I mentioned, by reverse iontophoretic, but this needs 15-20 minutes in a single analyte. The microneedle, there is no delay and have multiplex capability. So these are individually addressable. This is 12 millimeters square. We have 12 sensors. Each of them is individually addressable. You have glucose, lactate, alcohol, ketone, and so on. All of them are individually addressable. And these are penless, all 1 millimeter under the skin. You can monitor multiple biomarkers, either kidney biomarker, diabetic biomarker, all in a minimally invasive multiplex fashion. So this is our early work 12 years ago. This Josh Windmill, he founded BioLink, is now in Dexcom. He was a student. This was all on Microneedle in 2011, where we packed them with carbon paste containing the enzyme glucose oxidase. And this is in vitro calibration of glucose. This is the selectivity. You see no effect by ascorbic acid, uric acid, acetaminophen, very selective. So this was a long way. This is what BioLink is doing now. We use it also as a self-power sensor. When we use the microneedle as a biofuel cell, this is the anode for glucose, and this is the cathode for oxygen, and the power is proportional to the fuel glucose concentration. So it is a self-power sensor. We'll talk about energy in a few minutes. So one of our major activities for diabetic, again, using the multiplex capability, again, 12 millimeter force sensor, glucose, ketone, lactate, and alcohol. For closed loop, you want to have as much information. Not only this, you want to get insulin, you want to measure blood pressure, but this is the beginning of glucose and ketone, a major activity on ketoacidosis. And this is again simultaneous measurement of glucose and ketone plus alcohol, all influencing the insulin secretion. So it's important to follow all of this for optimal management of diabetic and dosage of insulin. So the vision is to add more microneedle, not only for glucose, lactate or ketone, but also adding cortisol, potassium, insulin itself one day, and glucagon is an insulin analog. This was reviewed recently our lab in Nature Review in the college, but this was a review about insulin. So in the future, we'll incorporate the insulin using aptamer as well as cortisol. So some of them will be using aptamer, other are ion selective electron, the other are enzyme. So you can combine different receptor, enzyme, ionophore, and aptamer on a single microneedle platform. So in this case, we have dual analyte, the ketone and the glucose. Again, one is the beta-hydroxybutyrate. This is the main ketone biomarker. Here we use dehydrogenase, HB dehydrogenase, so you need to immobilize NAD+ and a mediator. Here we have the glucose oxidase. So one sensor, you measure the peroxide. Here you measure the NADH product of this. And there is, again, no crosstalk between this is the HB sensor, addition of 2 millimolar HB, and this is the same for glucose. So there's a lot of interest, not only for diabetic, also for wellness and nutrition, the keto drink and following the ketone in the blood or saliva or ISF. So again, these are examples, ketone, glucose, and lactate. On the same patch, you have, again, this is the selectivity of the ketone sensor, the calibration. This is the glucose one. This is the crosstalk. This is the lactate. Again, the all lactate is also oxidase. So here we have the dehydrogenase, and there are, again, no cross between the three sensors, glucose, lactate, and ketone. And as I mentioned, for cortisol or for insulin, we will move to aptamer. So here is the first example of microneedle with aptamer, collaboration with Netzer Royo from Johns Hopkins. So this is the aptamer. This is for a drug antibiotic in a small animal. We show that we can follow this conformationally changing aptamer when we have a redox group, methylene blue. So upon binding, this folded, and you can see the analyte, again, continuously. Unlike antibody, this is continuous measurement using rapid square wave. And this is the first one example of company licensed in Nutromics in Australia developing this aptamer-based microneedle. Again, for Parkinson, we continue with levodopa continuously. And here we have multiplex capability. We have one sensor is non-enzymatic, does direct oxidation of levodopa. So this one is non-enzymatic by square wave voltammetry. You see the stability of the levodopa and the calibration. These are 2 micromolar addition. And this one is the enzymatic one with tyrosinase. We measure the dopaquinone amperometrically, and again, the stability. So here we have multiplexed when you do both non-enzymatic and enzymatic down to micromolar level of levodopa. Again, for a closed loop, for optimal dosage of levodopa for Parkinson patients. So we are integrating all of this on with the supporting electronic, with the battery, all wireless communication. So this again, 1 millimeter, minimally invasive. We're getting more sophisticated. This is a word from another spin-off company. So here we have very advanced electronic with the battery. Again, in this paper we show lactate, alcohol, glucose, and a few more. And this is electronic is reusable. You can see the parts. Again, this is look like a pen, but you have wireless electronic, which is reusable. Only the microneedle are disposable for after 3 days. So we use the microneedle for 3 days, the electronic interface, the battery, all wireless communication. So you see the two parts. This is the electronic with the energy here, and this is the single-use disposable sensor array. These are the microneedle, nice interface with these 4-5 pillars connect to the different metabolites. So this can measure 4 metabolites. You see different contact, reusable electronic, disposable array after 3 days. And again, it's all placed at 12 millimeter diameter. And this again, a spin-off, 3 companies spin-off, the BioLink doing the glucose, Nutromic do the aptamer. There's a new company also licensed the later generation. So 3 generations, 2011, 2017, 2021. Now all of this need the energy, so we have need a lot of power. We cannot carry this big solar cell, it's too big for our microneedle, so we need to shrink the energy, addressing the energy demand, storage, and harvesting. So initially we started with energy harvesting from the sweat lactate. So this is self-powered biofuel cell, this is the glucose, and you see increasing the power proportional to the glucose concentration. Very nice calibration. And this is always stretchable. You see 300% stretchability. This is the oxygen cathode, and this is the glucose anode with the naphthoquinone mediator. Stability under stretching. This is the calibration, increasing the concentration, the glucose fuel, very nice calibration under stretchability. You can power LED or watches. So it's a self-powered glucose sensor, nice power signal. You can see a higher power up to few milliwatt using this biofuel cell with lactate oxidase pellets. Again, this is the island bridge. I talk about the island bridge. You see these bridges are stretchable. This is 2 centimeters square or even more. You can get few milliwatt of power. You can see during exercise, see all flexible, and you get power of few milliwatt. To power different device like LED. And upon stretching, you see the power during the exercise from sweat lactate. So we harvest energy either from sweat biochemistry or mechanical tribo energy from the movement. Also, we remember the fingertip, there are a lot of sweat. You don't need to exercise. You can go to sleep and you get power because there is natural perspiration on the fingertip. So we extend it to day long or night long. We call it the power of dreaming, dream power. While you sleep, you generate energy without any investment. This high return of investment because you don't do any exercise and you get it directly without any mechanical input. This is passive perspiration, natural perspiration of sweat with a lactate oxidase. So this was featured in the cover of Science and Nature, all about while you sleep, the device harvests energy. Your sweaty fingertip could power this, then generate multiple finger, multiply the power. So now we have to combine this harvester with the storage. So we need to store all of this energy with battery or supercapacitor to meet all the energy demand of this wearable platform. So early work 5 years ago, we developed this hybrid of BFC, biofuel cell with supercapacitor. So On the same textile, this is the biofuel cell, like a serpentine. The other side is the supercapacitor. So you can store the energy of the sweat, the bioenergy of the sweat stored on the device. You stretchable. This is the biofuel. This is the supercapacitor side. The other side is the biofuel cell. You can see it here, highly twistable, highly stretchable, and you can get all this energy of sweat and store it on the supercapacitor. Here is the biofuel cell with the serpentine, the anode and cathode. Again, highly stretchable of the serpentine, bendable and twistable and so on. And you can also move to batteries, better storage, develop variety of zinc, silver oxide battery, high-powered battery, again, highly flexible, high performance. So again, you store, these are textile-based zinc, silver oxide batteries, replacing the lithium. We don't have the safety issue and the weight issue of lithium battery. And even this you can combine with energy harvesting. So we now use batteries developing like a grid. This is a mini grid where you have a multiple biofuel cell with the zinc silver oxide. So you have this complete grid, BFC battery. So you can store all this energy. This is large energy with all these 12 biofuel cell. And so you extended this for a continuous 24-hour operation. And this is another multimodular grid, not only sweat, but also mechanical energy for movement, TE and G. So you have a textile-based multimodal grid. So you can always have energy, either you're moving or not moving, and you store it on supercapacitor or on the batteries. So the goal is independent of your daily activity. You have mechanical energy from the tribo energy or biochemical energy. Here you're moving, you got the sweat is starting here, you get both mechanical energy and bioenergy. You stop the movement, the mechanical energy going, but you still have the sweat. So you have it all the time. And then we combine all of this for fully integrated, also an electrochromic display, P.PSS, where you display the level. These are the sensors, these are the batteries, and they also have this electrochromic display, as you'll see. So you get a fully integrated wireless system. You can see the design. These are the two batteries on the display. You see this 5 pixel tell you this 5 millimolar of lactate sensor. So I have the zinc silver oxide battery, electrochromic display, the sensor, the microcontroller, all also this is the display is from P.PSS, showing with the lactate level. Again, these are multi-layer, these are exploded view of the multiple layer. Again, the very advanced microcontroller. All again, you see the change of the color of the display with the lactate concentration, all under stretching and bending. So it will feature in nature electronic. So example again, repeated stretching, repeated bending, and this is again, you touch it with the sweat, you see the level of lactate is changing with the color change. So we have now fully integrated system with the energy and the display. So all this capability, and I hope I gave you a flavor, that we have now a variety of chemical sensor platform following both metabolite, electrolyte, hormone. We do a lot of security. We mentioned nerve agent yesterday, so we have a lot of defense application, and then combine it with other modality like blood pressure, and ECG, or temperature. So we are fusing the chemical information with the physical one on a single device to get a more comprehensive information tracking of the individual wellness, nutrition, or health. And hopefully this will lead to self-care, personal nutrition, personal wellness, remote medicine for continuous monitor, both chemical and physical parameter. And we are combining it now with smart home. This just came out in Nature Medicine, where all this chemical sensor will be integrated with smart home for the elderly, a lot of other surveillance devices like smart mirrors, smart salts. So not only look at the chemical sensor. This is the glucose, this is the vital, but also having mirrors all the cloud and smart robot system and social robot for a really future of elderly care. As you can see in this big review in Nature Medicine. So it's not only the sensor, the big cloud for processing this big data combined with other surveillance for future healthcare and healthy aging. So hopefully I gave you a flavor of our capabilities, a group of 40 people. It's our Christmas party, San Diego Bay. And again, a very dedicated group of postdocs, students, and visitor. And again, funding from different agency, center, and dedicated students. Thank you very much. Thank you for your attention.